Hey everyone, this is Aurora with Supercharged Science, and today we are going to be doing a class in solar astronomy. So if you like this and you want more, you want to go to my website, www.superchargedscience.com/astronomy, and you'll be able to download a packet of more astronomy lessons that I've put together that you can do with your homeschool kids, right from home. And so again, this is Aurora with Supercharged Science, and we're going to be talking about some solar astronomy. We've done a number of astronomy things lately. We just did planetary astronomy. We did some solar observing when Mercury was transiting the planet. So we're going to actually dive more depth into the different types of astronomy, and we're going to just focus on different types of stars. So, and before I forget, if you really like what you see and you want the entire class, because we're just going to do a small snippet of it, you can actually go to my website, superchargedscience.com/easy. Like, wow, that was so easy. And you can actually become a member of my online science program, and it's got the entire, I think it's like 2 hours long, course in solar astronomy. Okay, so let's get started. So solar astronomy, so when we study astronomy, there are many different areas of astronomy, and it's not just stars and pretty pictures, right? There's a lot more that's going on. And so we're going to focus on the astronomy that's particularly has to do with light. Now, most of astronomy has to do with light, but so let's clarify exactly what light is, okay? Now, by the way, before I forget, if you have a question and anytime you want to ask that question during class, you can always type it into the comment box that's right next to this Facebook Live video. And so I'll be stopping periodically so I can answer those questions. Oh, and we'll be probably going for about 15, 20-ish minutes, maybe a little longer, depending on how much we get into our content. You guys ready? Okay, so what is light anyway? Remember I just showed you a slide of it. What is it? Tell me out loud. You got 10 seconds. What is light? What do you think? Yeah, light is energy that can travel through space. How much energy that light has determines what kind of wave it is, whether it's visible, X-ray, radio, microwave. The electromagnetic spectrum, light, shows different types of energy of light and how that energy relates to different colors, different frequencies. You ever played with like a prism? Yeah, what happens? Like this, right? You get rainbows. The question is why? Okay, so prisms unmix the light into their individual wavelengths or their colors. You see this in a candle. We're actually looking through a prism. Actually, we're looking through several prisms stacked together called a diffraction grating. We'll talk more about that later. And we're actually looking through that thing to see a candle. So what color is the flame itself? Yeah, it's kind of whitish yellow, right? Okay, so what colors make up whitish yellow? Well, red, orange, yellow, green, blue, purple, right? You can see it right there. Good. Okay, so white light has all the colors of visible light at the same intensity. But if you have one at a different intensity, say you have much more green than anything else, what would happen to the light? Yeah, it'd have like this greenish hue, right? So green is a color or it's a wavelength. So wavelength is one property of light. Okay, so if you can think about like a harp, that's probably something you're more familiar with. Sound waves like from a harp. For example, imagine I've got a harp here in my hands and the harp strings go from long on one end and short on the other, right? Okay, so the long ones are going to be a low frequency, right? You'll hear boom, boom, boom. That's like red and orange colors that you can see. Now the medium, boom, 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 are like the yellow and the greens. And the higher ones, the boom, 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 this would be like blue and violet. And if you're way up here, it's like blink, 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 blink. Now we're getting into ultraviolet, and this is beyond what we can see. So the waves of light in a rainbow are like the notes on a harp. As we get longer, our longer strings, the sound we hear is lower. So the wavelengths are going to be longer, so the color is going to be more red. So that's what we mean by wavelength. Now you and I as people, we don't detect most wavelengths, most electromagnetic waves. There's light waves zooming around all over the place right now, but most of it you can't see. Our eyeballs can only see between 400 and 700 nanometers, like this little teeny spectrum. So this is all the possible wavelengths, and this is all we can see. So most of it is going to be invisible to us. So in fact, our eyes are actually tuned for green, which is why if you ever played with like a green laser and you see like the beam coming out, but if you play with a red laser, you only see like the dot on the wall, there's like no beam. It's because your eyes are tuned for green. Now, if your eyes were tuned for red, then you would see the red beam when it comes out. Okay, good. So other properties in light include intensity. are stars that are brighter closer to us? What do you think? Here's a picture. Some of the stars are brighter. Are they closer? Well, imagine this. If I have a car headlight and I have a teeny tiny little flashlight, and I have a big car headlight and a tiny little flashlight, and I shine them both at you, and I'm holding both of them so they're both about the same distance from you, which one's brighter? Yeah, the car headlight, right? So which one's closer? Well, you can't rely on intensity to tell you that. Does that make sense? Just because the ones that are brighter doesn't necessarily mean they're closer. It could, but it also may mean that they're more luminous. They're generating more light, more photons. Okay, so in fact, one of the first techniques that astronomers used was called triangulation, also known as parallax. So here's how it works. So the Earth goes around the sun, right? It orbits the sun, and it has a diameter across. If you were to take measuring tape and go from here all the way to this side. So this is the path the sun takes around. But if you were to measure the diameter of that orbit, it would be about 300 million kilometers, about 186 million miles. So by looking at a star on one day and then waiting 6 months and looking at the star, 6 months later, an astronomer could see a slight difference in the viewing angle for that star. With a little trigonometry, a little math, the different angles could yield a distance for you. Now, this technique still works today, but the stars have to be within about 400 light years of the Earth, which is basically like an inch in astronomy. Now, by the way, light year doesn't mean time, it means distance. It's how far light can travel in 1 year in space. So it's like a foot or a mile or a light year, okay? So there are known stars, let me show you my slide. There are known variable stars known as the Cepheids, which pulsate in and out like a heartbeat, dun, 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 right? They are really common. So no matter where you look in the galaxy, there's usually 1 or 2 of these things in the neighborhood. They pulsate over the course of days, like dun, dun, over like 1 or 2 days, or it could be even longer. Now, the longer it takes between the pulses, the brighter these stars are. And the shorter the period, the dimmer the star is going to appear. But for this to work, though, astronomers first use parallax to get the distance to close Cepheids, and then they calibrate a Cepheid's true brightness, and then they use that to compare with the Cepheids to stars who are more distant. So Cepheids are what we call really bright stars, so they're visible in galaxies that are tens of millions of light years away. So they will actually use Cepheids, which are pulsing stars, to try and figure out the brightness of other stars that we can't use parallax for. Now, it also turns out that a star's color spectrum, like the color that we get from the star, is also a good indication of how bright the thing is. So the relationship between color and brightness, that's figured out using stars that are closer to the Earth that have their distances measured directly. So when astronomers look at a really far away star, they can measure the incoming light and then determine the star's actual brightness because they already know what it's like for the ones that are nearby. And they also know what they can expect to, how far that star could, that light is going to dim on its way to Earth. So they can actually use that to calculate the distance of a star. Isn't that cool? Okay, so how do you know, you know what, let's skip this part because I want to show you something else. Let's see. Okay, here's a picture of the sun. 2 scientists, Bunsen and Kirchhoff, both discovered that the sun's spectrum was different than the rainbow you get using the prism and a light bulb, like we just talked about with the candle and the prism. Rather than being this beautiful continuous spectrum, it's filled with all these little black lines. You see those? So each shade of color represents a specific wavelength of light, right? Like red and orange and yellow, right? But the black lines, those correspond to missing wavelengths of light from an otherwise continuous spectrum. Like this thing should be continuous. There should not be any black lines like anywhere, but there are. And that tells us which wavelengths are blocked or missing. So there are 2 possible explanations that account for these missing wavelengths, right? So guess number 1 that they had was, well, maybe the sun doesn't emit, wavelengths of all different colors, of all the different wavelengths. Maybe it doesn't do them all. Maybe it just does some of them, right? The black lines correspond to the ones the sun doesn't make. The second one, though, is the sun actually does emit all wavelengths, but there's something between the sun and the Earth that is absorbing those out and filtering out certain wavelengths of light. So which one do you think it is? Do you think the sun just doesn't emit all wavelengths? Or do you think maybe there's something in between the sun and the Earth that are kind of like sucking all those up? What do you think? It's actually number 2. The sun's atmosphere is actually what's causing those missing wavelengths. And that's what causes those black lines. So as the light passes through the Earth's atmosphere, certain wavelengths are filtered out. Now, so this produces the black lines you see here, right? Okay, so we call those, the water actually specifically in the atmosphere absorbs certain wavelengths of light, which corresponds to the black lines. So when astronomers look at stars, they have computers look at them. They don't actually look at them. Very rarely, people don't know this, but most astronomers do not look through telescopes. They have computers that do it for them because it's so complicated. And I'm about to show you how complicated it can get. So what they'll do is they'll have a computer and they'll take a picture, and then they will spend a lot of time with the computer trying to make sense of what they've seen, of all the data that they've taken. So when astronomers look at stars, the computers are put up to the end of the telescope. And so here's what they see. Okay, so what we saw was an absorption spectrum. Okay, and notice how these two are kind of like a puzzle, right? Does it look like they'd fit together? So what's the difference between these two? Okay, so the upper picture, that's the absorption spectrum of hydrogen. This is what you'd see if you looked through a cloud of hydrogen at a light source. You know, you've got like a campfire or a candle, and there's a cloud of hydrogen and you're looking through it. This is what you would see. You would see these black lines that hydrogen is absorbing these particular wavelengths. So what's the thing on the bottom? Okay, this is an emission spectrum. This means you take that cloud of hydrogen and you energize it, you make it glow, and these are the wavelengths of light. This is what color that cloud of hydrogen is going to glow, and it actually magically gives you the ones that it actually absorbs. Same pattern, but it's a different way of getting the same information. So these are the wavelengths that are missing from a continuous spectrum. Isn't that cool? Every element on the periodic table in its gas form will filter out certain wavelengths of visible light. And the black lines that are created by each element, they basically are what astronomers think of as a fingerprint. It's true for gold, it's true for silver, platinum, arsenic, iodine, all of them. All right, so now you're an astronomer. Why would you want to know about this kind of chemistry? Well, you can use it because now you have a way to detect which elements are present in a star. You can also use it to detect the atmosphere of a planet around that's maybe orbiting around a different star, if you can catch some of that sunlight that is going right through the atmosphere of another planet. So astronomers look for these missing frequencies, and if the light frequencies correspond to, say, methane and carbon dioxide are missing, then the atmosphere, they know, contains methane and carbon dioxide, because those are the things that absorb the missing wavelengths, right? They do have to wait till a planet crosses in front of the star, and then they look at how the light changes. And they can also detect the light from the star when the planet is behind the star. They can tell a difference. So if so far astronomers have detected water on several remote planets using this method, as well as detected things like sodium, carbon dioxide, and silicates, and many more. They also look for signs of pollution signatures in the spectra. Okay, so every element in the periodic table in its gas form will filter out certain wavelengths of light, and black lines are created, right? Okay, so, oh, wait, actually, let me show you a different spectrum. Here we go. So imagine we superimpose all of these. So these are spectrums. So a chemist was in a laboratory and he made a cloud of hydrogen glowed. He put it through a little an analyzer, and he realized, hey, these are the wavelengths, and he got that. And so he did it separately for hydrogen, helium, nitrogen, and oxygen. He got all these different wavelengths. Okay, and now how is that useful? Because most stars are not, or actually pretty much all stars are not just going to be just hydrogen or just helium or just nitrogen. They're going to be a combination. And this is where astronomy gets really complicated. So this may be what you get from a star, and it doesn't match any of these. But using a computer and running some data analysis, you can say, oh, you know what? This is actually hydrogen plus helium plus nitrogen plus oxygen. All four of these are in that incoming light that I'm receiving. And you just break it apart like a puzzle, right? So the solar spectrum is basically the sum of all the different lines from different elements. So an experienced astronomer can decipher this code and determine which elements were present in the sun's atmosphere. How cool is that? Now, not all light is going to give the whole rainbow. It depends on the light source itself. Now, sometimes you're only going to get red, sometimes you get green, sometimes you'll get yellow and red. So it just depends. So for example, this one's hydrogen. This is a real photograph of what you'd see if you made the hydrogen glow and you look at it through a special filter. This is a neon open sign. This is a mercury lamp, okay, and this is actually what you'd see. And this is a sodium lamp down here. Isn't that cool? Okay, so let's take a look at some real data. Now, so this is some real data from certain elements in here, and it shows you actual data. So this has an emission line that happens right after 1200, and this is hydrogen. Notice helium has one at 1200, but it's not nearly as high as the one for helium. So helium's 1200 emission line is not as strong as the one that comes after 1600, right? And the one for krypton, this has nothing to do with Superman. This has something to do with science. Krypton gas doesn't have one around 1200, but it has one here and here, both sides around to 1200, but not quite on it. You see how they're different? Okay, so would you like to try some real data? Do you want me to show you some real data from a star, and we'll see if we can figure it out? So check this out. This is real data from the atmosphere of a moon. Okay, and so here's a picture of the moon, and this is what we have here. So we have this really tall spike, super tall, and then we have a whole bunch of noise, right? So what do you think it might be made out of? Here, let's go back. So we got a spike at 1200 and then a bunch of noise. So this one has a spike at 1200 and a spike at 16. So if there was helium, we should expect to see another spike at 16, but we don't. So what do you think? Yeah, so this atmosphere is going to have hydrogen in it, and it's going to have a whole bunch of noise that looks like this, which happens to be nitrogen. So we have hydrogen and nitrogen in this, this is actually a moon, the atmosphere of this particular moon. Isn't that cool? So here's a spectrum taken from Saturn's rings. So let's see if we can figure out what Saturn's rings are like. Okay, so we'll take a look. You see a spike just around 1200, it's huge. And then we see a whoop up at the end here, right? Okay, so what can you already tell me? Yeah, that one at 1600 is missing. So you know this one's probably hydrogen. There's hydrogen present. Okay, good. And you've got some stuff over here. So this may be another combination of different elements that are here at the end, which I actually didn't show you yet. Okay, so Titan is the only moon to enter in the entire solar system to have a substantial atmosphere. And it's mostly nitrogen gas like the Earth's atmosphere, but it's got some differences too. The temperatures are actually really cold on Titan. There's no oxygen to breathe and so forth. But this is an actual spectra taken of Titan. Now Titan's atmosphere is actually really complicated, so I'm showing you this. So we can actually see, and scientists have already labeled what the different element spikes are, and they can actually tell. And they've used a computer to figure this out. Okay, so we have our hydrogen, part of our hydrogen spike here, and then we've got several other elements. We have carbon dioxide, and so forth, and all these other methane type compounds in here, hydrocarbons. So how are we doing so far? What do you guys think? Let me pause just for a minute and see if there's any questions. Well, no questions come in yet. That's okay. That's okay. If you, my name's Aurora with Supercharged Science. You know, if you like this and you'd like some more real hands-on astronomy lessons, make sure you download my free guidebook from superchargedscience.com/astronomy. So you just go to superchargedscience.com/astronomy and you can download my astronomy lessons there. Okay, so one of the things I wanted to talk about really quick is, I know we've gone a little bit over, we're like at 20 minutes already, but I wanted to talk about Doppler Shift really quick with stars. Okay, now you know if you've ever been standing on a corner and like an ambulance comes by, you hear doo 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 doo, and then they pass you, and then what does it sound like? Does it change? Yeah, it goes like doo 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 doo, right? It changes, and it changes because in the beginning, here's a slide so you can see it. As the sound waves are coming towards you, so this thing is making sound waves, right? And they're emanating out. But if the sound waves are traveling, they kind of bunch up in the front and spread out in the back because you've got a moving source of a moving wave source. And so that's why in the beginning they're higher pitched because the waves are closer together. And when it passes you, they're further apart. And that's why it sounds like the waves are going further from you. Now, this shortening of wavelengths at the front end and lengthening of the wavelengths at the back end, that actually happens with light as well, especially if you have a star that's moving. So if we have a star and we're looking at it at night, how do we know whether the star is coming closer to the Earth or maybe it's moving away from the Earth? Well, what we do is we can actually detect what we call a blue shift or a red shift. And a blue shift is when the things shorten, when the wavelengths shorten and it's coming towards you. And if something is red shifted, it means that it's the object is moving away from you. It means you're over here. Okay, so that's something that we can actually change, we can detect, and the wavelengths all themselves change. So this Doppler effect works for all kinds of waves. It doesn't have to be just sound waves. It could be visible light waves, it could be water waves, any kinds of waves. So the star, imagine the star, it's like not moving towards the Earth at all, okay? So if we looked at the spectrum, it's gonna look like this, right? It's just staying put, it's just the same. This is what it would normally be. Okay, now imagine the star begins to move slowly towards the Earth, right? So now that absorption fingerprint line is actually going to remain the same, but it's going to be shifted more towards the blue end of the spectrum, okay? Now, which one of these is going to be shifted towards? Okay, so it's going to be, this one is going to be, if it's moving towards, and this one is it's going to be moving away. Now there's more information here that meets the eye. Notice how one of these is shifted way more than the other. Yeah, this one is shifted more than this one. Look at where it usually is, or where it is when it's not moving. So this one is right between, it's more on the green than the yellow, and we just shifted it a little bit. But look at this, we shifted it like a lot. So this tells you the star is moving fast and it's moving towards you. This tells you the star is moving slow and it's moving away from you. Isn't that cool? So that's red shift and blue shift. You can also use Doppler effect to determine the rotation of stars. Now the Doppler effect is used to determine, imagine like a star is rotating on its own axis, you know, so we're looking top down, the thing's spinning like this, okay? So it's not approaching or going away from the Earth, but we can just see it kind of spinning like a record player. Remember those? So what happens is the left half of the star, okay, so Earth is here, okay, and we're like above the Earth, looking down on the Earth and the star at the same time. The star is not moving towards or away from the Earth, but we can just see both, okay? So we kind of have a bird's eye view here, or a space bird's eye view. Okay, so what's happening is, as this thing is rotating, the left side here of the star is approaching the Earth, and the right side is receding away from the Earth. You got that? So we're approaching, and then we're receding. Okay, so the light from one side is going to be shifted one way. The light from the other side is going to be shifted the other way. Does that make sense? It's going to be blue shifted here, red shifted here, because the back stuff is coming towards you and the towards stuff is going away from you. What does that mean? So that means we can tell the rotation of certain stars depending on how they're shifted. But remember, a star is not like the Earth. It's not like a solid chunk of rock. It's a gas ball. So not all the points on the star approach and recede at the same speed. Didn't I warn you astronomy was like really complicated and it quickly like gets out of hand? This is where it goes a little crazy. Stick with me though. So the far side of the star is going to approach the fastest, and a point that's kind of in the middle is going to approach a little less, and the point near the center is not so much. So instead of all these lines, you're going to get like a bar here. And so does that kind of make sense? So a middle left point is going to approach more slowly, and it's just moderately blue shifted, and the front of the star is going to be totally out of sight. It's not blue shifted at all. It's going to be it's going to be looking right at you. So the same is true for the other side. And so I only chose like 5 points here, but really you could have like hundreds of them. So instead, it's going to appear as a solid bar. And the faster the star rotates, the bigger this bar is going to be, right? Because the more shifted those outer points are going to be. And the slower it rotates, the narrower the bar. And this is like barely rotating at all, okay? And if the star were just like to stop, you just get like a single line. So if you have a lot of emission lines in here, you can tell that, ooh, that thing is rotating really fast. Okay, so now you tell me, let's put all the pieces together. What's happening to each one of these, okay? So sometimes stars are going to show a combination of motions. So things aren't just like one or the other. It's like everything happens at once. So you could have a star rotating while moving towards the Earth or away from the Earth, or it could be rotating fast but not moving towards or away from the Earth. So that bar is going to be in the center. Okay, so let's take a look. Where did I put my slide? There it is. Okay, so here we go. So if the thing is not moving towards or away from the Earth, but it's just rotating, it's going to have a bar like the top. But what's going on here? So this is a star that's rotating, but it's moving. Is it moving towards the Earth or away from the Earth? It's moving towards the Earth because it's blue shifted. It's like gone over to the shorter wavelength, so it's coming towards you. And so this one is going away from you, right? It's rotating fast and it's moving away from you. So if you think about all the unlimited possibilities here, the unlimited possible rates of rotation, how fast the approach speeds are or the recessional speeds are, you can see there's like an unlimited number of combinations of red shifts and blue shifts, and you'd really have to know what you're looking at, right? And then it all changes depending on if this star is emanating this kind of light, or maybe it's generating this type of light, maybe it's got more oxygen in its core, maybe it's got more hydrogen in its core, so it's going to be different. And so that's why astronomers have to study so many things. They have to be really good at physics, they have to be really good at chemistry, and good at a lot of different areas because they all intersect and combine into one really cool application called astronomy. Let me show you one more thing before we finish. You can actually use Doppler Shift to find out the mass of a planet. You can actually detect a slight wobble in the velocity of the star as it's being tugged on by a planet as they both orbit a common center of gravity. So they can actually do this just for really slow speeds, like detecting an Earth-sized planet around a star like of Neptune. So if a star is moving, and have you ever had like a sack of potatoes in your hands, or like an orange, or a bag of oranges or something, and you're like a kid and you like start zinging it around? You know that if you've got a really heavy sack, and kids don't weigh nearly as much as grown-ups, really heavy sack, and you kind of swing it around and around, and both of you are going around, you know that you have to kind of set back a little bit in order to stay balanced, because if you're still straight up and down and you've got this really heavy bag, you're going to get yanked over. The same idea here. So when where'd the slide go? So as this planet is going around this sun, it will yank on that star ever so slightly, meaning that star will come a little bit towards the Earth and a little bit away from the Earth, depending on where the star is in its orbit. And that shows up as a shift, as a red shift and a blue shift. Initially, the astronomers were like, oh no, there's even more shifting going on, and I don't know what's going on. And then we realized, hey, you know what? That's actually star wobble. All right, well, I'm going to pause here because we've actually gone really, really far. We've done a real in-depth look at astronomy and spectroscopy. Now, if you like this and you want more, you want kids to build their own calibrated spectrometer where they can actually measure the nanometers of light that's coming off of anything they look at. That's actually in my online eScience program. You can learn more about that program by going to www.superchargedscience.com/easy. Like, wow, that was so easy. I don't have to know this stuff. She's teaching it for me. This is fantastic. So you want to go to www.superchargedscience.com/easy. There's a video on that page. It'll show you the program. It'll show you what it outlines. It's got everything in it. It's for K through 12, astronomy, biology, life science, chemistry, physics, you name it, it's on there. Kids get to build over 2,500 projects with that program alone. There's a huge amount of projects on there. The ones for astronomy, there's over 250 projects just in astronomy, and the what we just covered is part of one of the content pieces that's in astronomy. And so if you want to build there's I think 3 different kinds of spectrometers that you can build. We also teach you how you can take a campfire and color it, and so you can use your calibrated spectrometer to look at the different colors depending on what you do to your campfire. So there's lots of really cool experiments that are hands-on, they're real, they're applied. So if your kids are bored with their current science curriculum, or they're rolling their eyes, or they don't even know what am I going to use this for, right? Because if I had just started talking to you about spectra and emission lines and nanometers and wavelengths, you would have been like, yeah, who cares? You have to also have the application with it. And so that's what the program is based on. So all of the projects in there are hands-on. They're real projects developed by astronomers, pilots, engineers, you name it. They're all in there that have been working together, and mostly it's me, but I also bring in experts where and when we need it. Okay, so if you like this and you want more, I look forward to seeing you in our next one. Download those free lessons that I put together. I think there's like 4 or 5 of them in astronomy. You get those from my website. There's a link right next to this YouTube live video. YouTube, where are we? No, we're on Facebook, sorry. And if you'd like to join me and just do a risk-free 30-day trial, there's no strings attached. If you try it and you like it, you stay with us. If you try it and it's not for you, you just request a refund within the first 30 days and it's totally risk-free and you get your money back. So you can try that as well and see if it's a good fit for you and your family. But I hope this has been helpful. Make sure you share this information with as many people as possible because we want to make sure everybody has access to top-notch world-class education, and we want to empower our kids for the future that they're going to be building for us tomorrow. So I hope this has been fun and helpful. If you do have any questions, feel free to ask anytime. I'm Aurora at superchargedscience.com, and I will see you next time. Take care, everybody.